Hello, how are you? I'm in the middle of 21 flights in 21 days. And I got myself sick last on Saturday in the middle of these flights. And this is my first time I've actually been standing speaking since. So it's going to be good for you because I'm going to speak more slowly. Anyway, a little bit of background. I spent my entire life designing, architecting, and deploying software systems. My first software company went bankrupt when I was 20, and then I lived in my car. I started my second company called Systems Research and Development while I lived in my car, and that company turned out to grow up okay. I've personally designed and architected about 100 different systems over the years, and about 5 or 10 of these systems are multi-billion row, multi-hundred million person type systems. I moved my company to Vegas right around 1990. I spent about a decade building software for the casinos in Las Vegas. Today, half the casinos in the world still use one technology or another that I built. One of the systems that I built was used by the surveillance intelligence arm for gaming, and that system was used to help catch the team called the MIT card count team. So there's a book called Bringing Down the House and a movie called 21. I built that infrastructure that brought those little bastards to their knees. They thought it was the facial recognition that I deployed in '96, but that was a lie. Maybe more about that in questions and answers. I built this other technology for the casinos that became known as NORA, Non-Obvious Relationship Awareness. When a casino can lose $250,000 in 15 minutes, they're not very interested in batch jobs running end of day. So they wanted to very quickly be able to detect if there was any risk right at the minute it was happening. And of the 100 things that I invented, that was the only thing that actually turned out to be valuable, because that's the reason why IBM came along and bought my company. But before IBM bought my company, I took a round of venture capital from the venture capital arm of the Central Intelligence Agency. And that was interesting. It was before 9/11. The work I'd done for the casinos, we were helping the casinos find employees who were corrupt. And when this group called InQtel came to fund us, their interest, and this is again before 9/11, their interest was finding criminals in the government. So I thought, that was kind of cool. So I agreed. I hired a CEO to run my company. His very first big decision was to tell me I was not a very good chairman of the board. So I demoted myself to vice chairman, and we brought a real chairman of the board in, and then they sold my company with my agreement. IBM buys my company in January of 2005. No one thought I would stay. Been at IBM for 7 years. I'm having a good time. I have no sales quota. I have no billing rate. No one reports to me. So I'm having a good time. My job's my hobby. Today I work on how can systems make sense of data as it's happening, and how can you do that with higher levels of privacy and civil liberty protections at the same time. So I work with some privacy groups. So I not only help my government on one hand, but I sit as an advisor on some privacy groups where we sue the government. Very dangerous. To help both. The tough part about building systems that make sense of the world is that as computers are getting faster, organizations are getting dumber. And what's happening is the observation space that's available to an organization is growing on one curve, and the ability for organizations to make sense of it has not been able to keep up. And if you think it's bad today, Eric Schmidt, about 18 months ago, said every 2 days we create more data than the beginning of mankind until 2003. And what's happening is, as this widens, organizations have what I call enterprise amnesia. Amnesia means to be forgetful. It's like having a red puzzle piece in this hand and a blue puzzle piece in this hand, but the organization can't see both. So they make dumb decisions. We did some work for a large retailer in the US. We showed them that 2 out of every 1,000 people they were hiring had already been arrested for stealing from them at the same store. So that's ridiculous. So that's enterprise amnesia. And it's on the rise. I looked up amnesia in the dictionary. It says brain damage. So you can't really tell companies they have brain damage. So I made up enterprise amnesia to mean a defect in memory that results in wasted resources, lost revenues, blah, blah, blah. Now the question is, how come as computers are getting faster, we haven't been able to make computers even remotely keep up in making sense of all the data? I did a blog post about this called Algorithms at Dead End. You can't squeeze knowledge out of a pixel. And here's what I mean. If this is the only piece of data you have because somebody's just enrolled in a newsletter, I would argue that you could use an infinite amount of compute, time, and energy. And what's your ability to recognize whether this is good news or bad news? You can't. You could use infinite compute. So when I say context, what do I mean? I mean better understanding something by looking at the things around it. So when you see the word bat in a sentence, you look at the words around it to know what kind of bat it is. So when I think about information in context, I think about it like this. I think about weaving the data together from all the different sources, such that when this piece of data shows up and fits here, you could use an original 1983 IBM PC and make more sense out of this than infinite supercompute and infinite energy staring at just the yellow puzzle piece. So this puzzle metaphor, this puzzle example holds up really well. Today I watch the way people put puzzles together at home, and it inspires me on my algorithms that I'm working on today. So I want you to picture this for a second. In the middle of the room, a giant pile of puzzle pieces, different colors, different sizes, different shapes. There's no covers of the box. You don't know if there's 5 puzzles or is it 500 puzzles. Lots of pieces are missing. Some of the pieces are duplicates. There's lots of errors. And some of the pieces are professionally fabricated lies. Until you start taking those puzzle pieces off the pile to the table to see how they fit in with each other, you have to do that to get a real sense of what's going on. So I've been thinking about doing a puzzle project, and in fact I bought this puzzle and I hid 10% of the pieces. And then I bought this puzzle and hid a third. And I bought this puzzle and hid half. Then I bought this puzzle and only kept 2% or 6 of the pieces. And because I have a dark, twisted side, I bought a copy of the first puzzle. And I took 10% of the pieces out of there as duplicates. And I made a pile. This is just over a year ago. And this is at my girlfriend's house, and this is on her kitchen table. My girlfriend sees her son and 3 cousins. I see 4 parallel processing pipelines. I told them nothing. They just got started. This is the first 2 pieces of data that found each other. Here, more data is finding more data. Here, I can see this duplicate right here. They don't even know a duplicate is possible until they find this piece here. But the puzzle began to take form, even though it had so many parts missing, and even though they didn't have the cover of the box. They started at 6:40. 22 minutes in, they realized there was a duplicate. 35 minutes in, they said, I think some of the pieces are missing. 37 minutes in, they said, looks like a bunch of hillbillies on a porch. I don't know if you know the word hillbillies, but when I'm in Asia, I have to explain it. I tell them they live in the hills, they have no teeth, they make their own alcohol, and their family tree goes straight down. And then they look at me and go, oh, it's like everybody's got hillbillies, okay. About 8 minutes later, they modified that and said it's hillbillies playing guitars, sitting on a porch near a barber sign and a banjo. So under the bowl is the barbershop sign. Under there is the guitar, some boots on a porch, and to the right, a banjo. They made this estimation when they only had a puzzle that had 50% of its observation space. I've done 4 puzzle projects now where I've learned something from each of them. And in every puzzle I've done, when you get to less than 50% of the observation space, you can make a very good estimation about the scene. 47 minutes in, they realized no matter how much they wanted to apply effort to the sky or the grass, it was just sky or grass. They knew there was nothing more that was going to be learned, so they decided they wanted to take it off the table. 2 hours in, the oldest of them, the 17-year-old girl, said, let's switch sides and see if we can make sense of this from different perspectives. I thought she was a genius. I'm like, genius. I ran over and wrote it down. The adults in the room that were watching this thought I was bananas. 2 hours and 10 minutes in, wait, there are 3. No, they realized there's a 4th puzzle. This is very embarrassing for me. You'd think after having deployed about 100 systems, you could size the damn table space right. It turns out the 3 primary puzzles that took form wouldn't fit on the kitchen table. Looking back, I think 70% of every system I've ever deployed, I kind of misestimated this space. And it still exists, I guess. 2 hours and 18 minutes in, they realized I threw in a few random pieces. It was only a few minutes later, the oldest boy looked at me and just said, you're evil. And I gotta tell you, it was like a great day for me. I'm like, this is awesome. It was a highlight of last year. But the puzzle began to take form. So how does context accumulate? And the way it happens transactionally in an enterprise, and the way it happens if you have a box of puzzle pieces and take a puzzle piece out, the process is really very much the same. For every transaction you get, like a puzzle piece, you look at the table where you're putting the puzzle together and you make one of three assertions. You either don't know where the puzzle piece goes, so you put it anywhere, or it's like the red and white pieces, so you put it near them, or it attaches to something. And then that's the most you're really going to know. And then it's your chance to go on and get the next piece. When you attach a puzzle piece, you favor the false negative. You only put things together when you're sure. And you would never put two Jeff Jonases together, even if they both were from Las Vegas. There's another Jeff Jonas in Vegas who sells real estate. And when you put a puzzle together at home, you favor the false negative. When's the last time you put a puzzle together at home and you said the piece doesn't fit very well, but with some glue and a hammer, I can pound the sucker in there. You don't do that. You only put it in when you're sure. New observations sometimes reverse earlier assertions. In identity systems, you might decide two people are the same because they have the same name, address, and phone, but only later when a new record shows up do you realize it's a junior and a senior. And then you have to take it apart. This happens at home in a puzzle too. You'll figure out where a piece goes and another piece is fighting you. You realize you have to take it apart. This, by the way, is technically the hardest thing to do and uses the most compute in the work that I do. So imagine you've seen 1 billion puzzle pieces and you've made 1 billion transactional decisions about things that are the same and related. And now you get puzzle piece 1,000,000,001. At that moment, you have to say, now that I learned that, had I known that in the beginning, would I have made any decisions differently over those billion rows? Today, where I'm at on scale with that, with my existing stuff, is with roughly in the category of 10 billion transactions, about, say, 750 million people. It takes about, you can do only about 2,000, right now my best stuff can only do about 2,000 transactions a second, where every puzzle, every new transaction that arrives figures out where it belongs and fixes the past. That's on the 100 terabytes of solid state, by the way. But that's where the scale starts to get expensive, is changing your mind about the past with the evidence of every new single piece of data. I'm working on some new breakthrough methods that are going to change that curve so the scale's bigger and better than that. Some observations produce novel discoveries, like, if you were putting a puzzle together at home and it's blades of grass, it's just blades of grass, but it might be the one puzzle piece that connects two seams. Sometimes you'll find one very normal record, like a phone book record, but the name and the address create this connection between two things that maybe finds some fraud if you work for a bank. So this part here, I think, is the most exciting. When you put a puzzle together at home, can you put it together on the table this big? If the puzzle's going to be this big? No, it puffs up. The most expensive piece is when the puzzle takes the most space, because there's the most ambiguity. But if you have a sufficient number of puzzle pieces, you get this point where pretty soon you get the edges and the chunks start to fall in. And what starts happening is your confidence is increasing, and the amount of compute that it takes you to place the puzzle pieces the amount of compute is decreasing. And I saw this for the first time in 2006. I had a customer with 50 billion rows of data, not a government. A big marketing company in the U.S. had 50 billion rows of data. And after we ingested 3 billion rows, the system had a certain accuracy and a certain speed. But when it got to 8 billion rows, it was more accurate, and the computational cost of the next transaction was less. It has really profound ramifications for big data. The notion that the more data you get, the more accurate you can be, and the faster it is to compute. This leads to something that I call big data in context equals a new physics. You find when you do it this way, where you figure out how transactions relate to the prior ones, like puzzle pieces find their place in the puzzle, your false positives and your false negatives go down at the same time. That means the quality of your predictions get better. It turns out that bad data starts to become your friend. You'll be happy that you did not over-clean your data. I tell some folks, banks and insurance companies, for example, that are trying to find fraud, I tell them if they polish every puzzle piece to perfection, they will not find the weak signal. They're really skilled bad guys. When you search Google, by the way, and it says, did you mean this? It's not looking at a dictionary. It's actually remembering everybody's errors. And if it wasn't remembering the errors, it wouldn't be so smart. So I worry about some programs where they're trying to overthink the data when natural variability in the data can actually be your friend. And the third big data new physics principle is that the more data you get, the less compute it takes. And again, I think this is really fascinating. When I explained this to my mother, I asked her, why is it the last few pieces of the puzzle are as easy as the first few, when you have more data in front of you than ever before? And this puzzle metaphor holds up extremely well. Like I said, I've done four, I don't know if I mentioned it. If I mentioned it, I probably still have the temperature. Okay, moving right along. So there's a big difference between a pile of big data and then big data that's in context. And when I say in context, one of the first forms of context is what I call expert counting. As soon as you commingle data from different sources together, you better know the difference between 5 people each with one account, or is it one person with 5 accounts? Is it 20 cases of H1N1 in 20 cities, or one case reported 20 times? I can't tell you how many public sector and private sector organizations are trying to build big fancy graphs and visualization systems, or doing pattern discovery, or outlier analysis, or anomaly detection, and they first haven't expertly counted their data. Those activities flatten out early, like my green line, if you can't figure out if things are the same. You know, if you have one source, do you guys have Starbucks here? Yeah. This is great. I gotta find it. All of them. Okay. But one data source might have a Starbucks at an address, and another data source would say Starbucks 123, and another data source might have a latitude, longitude. If you don't know if those are 3 facts about the same place, how can you make high-quality predictions? So it turns out if you can't count, you can't estimate the vector that something's heading on its velocity. And without vector and velocity, it's very hard to make a prediction. So I have a little example of this. One form of counting identities, one could call entity or identity resolution. And I do some work in voter registration systems. We're trying to clean up the election rolls in the US. Here we have a voter on the left and a dead person on the right. And the only thing the same is the same as the name and the year of birth. But if you thought that was interesting, there's too many of these matches for humans to even review. So our election offices have access to our Department of Motor Vehicle data, the Blue Record. And this Blue Record has features of both. But let's say because of the middle initial, it has more features with the voter, so it snaps in. And now there's so many features on the voter side, including the year of birth and our social security number, that now, because of the name, the year of birth, and the social security number, a machine, no human, can make an assertion and properly count this and know it's the same. And when you can put these 3 together automatically, you find out that George, who died in 1995, voted in 2008. And this is only legal in 2 states in the US. As a joke, it's illegal everywhere. So my NORA technology that IBM bought, they renamed it to something ridiculously crazy for a few years. And then they fixed it and called it this. I have one example for you. This is one of the few projects I didn't have anything to do with, so it showed up in my in-basket as a surprise. MoneyGram does money transfers, like Western Union. And they are using this form of context accumulation where your predictions get better. And 2 interesting things that I read about this is the day they turned it on, their number of fraud complaints dropped 71%. Is that what it says? Does it say 70? 72. Okay. Anyway, their fraud dropped that. I wish I was in the call center that next morning. That would have been fun. The other thing that I think was more interesting is this little use case here tells the story of a 100-year-old grandmother, and she goes to Western Union to transfer, goes to MoneyGram to transfer $2,500. And MoneyGram, because they believed in their predictions so much that were being made by context accumulation, they told her, no, we're not transferring the money, we think it's fraud. And she said, it's not fraud. Talk to them on the phone, you will transfer the money. And MoneyGram says, no, we think it's fraud. And she's like, this is my time of need. I've given you my business for years. This isn't. And MoneyGram's not going to lose any money if they transfer it. It's her loss. They were so confident in their prediction, they still said no. And she calls back 3 days later in tears, thanking them because it really was fraud. And I think that's interesting. What's interesting to me about this is, and I'm starting to see this more and more, where the prediction of the computer is such that you can actually confidently override a human. And I would have said 5 years ago, never put a machine in that position, but you're starting, I think with big data, we might see this inflection where there's cases where you can do that. I think you have to be really careful in cases where it's like police pointing guns at people and things. So I have this vision now about how you make enterprises more intelligent. So down in the center here is what you already know. It's what you've been weaving together across your internal and your external data sources. And your observation space is more transactional data, it's mobile data, it's social data. And here comes a new piece of data. And this piece of data first figures out where it belongs. And I call that data finds data. And only after it lands do you make a decision about it and say, is this good news